Hello, can you hear me?
Yes, sir.
Yeah. So, sorry, I could not come to the last class because I was busy with something, some other things. So, so how was your exam, by the way? Hello.
Sir, it was quite tough.
It was quite tough.
Yes.
Actually, sir, it was quite long. There was, I mean, even 3 hours felt quite short.
Okay. I mean, other than the length, what was the other problem?
Oh,
You
yes,
solved
sir. There were some problems with question 8 and question 4. There had to be some corrections, and some people had spent a lot of time on that. So that was also a problem.
Yes, that was there. But the rest of them was kind of something that people could do easily.
No, sir.
Yeah. So question 8 there was a problem, and question 4 also there was a. What was the error there? Forgot something.
Sir, keeping these two questions aside, then also I find it very difficult to solve other problems also.
Okay. So I mean, can we kind of try to pinpoint what's the problem? What was the difficulty that you are facing? See, because other than that, 3 questions was from the problem set D2. Hello.
Sir, so the first and third were from the problem set. So which one was the third question?
The third
Was
question.
it?
You have to look at this. Least I have to look at this thing. Just one second. Give me a minute. I need to find out.
Sir, and the problem 6 involved some terminology called Dijkstra tree. Sir, I'm not sure, sir, did we discuss about this Dijkstra tree in
Yes.
class?
I mean, in all the examples and everything that was done, there was this tree structure that was coming up.
Yes, sir. So just wanted to confirm. So for the second part of the 6th question, the answer should be no, right?
Just one second. Let me just first open the question paper before I say anything. Yeah. For second part of this 6th paper, yes, answer will be no.
Because all the vertices may not be reachable. So that's the thing.
Okay, so I mean, even if you think of it, it's not about the reachability part. Okay, so even if you think of, so when we talk about this, so Dijkstra cat doesn't necessarily have to be directed, right? Dijkstra is also for undirected graphs. In fact, initially when we wrote this Dijkstra algorithm, it was for the undirected graph only. Right, so it's not the reachability issue that comes in.
So we can give a counter example.
Yes, you can give a counter example. So what kind of counter example can you give? Right. So
yes, so I used the square where the opposite vertices were directed. So the edges were directed to the opposite vertices. So if we start with any vertex, we cannot span the whole graph. So there was no way we can find a spanning tree.
So you start with the opposite vertex, you cannot span the whole graph. Sorry, with undirected graph.
So the directed one.
No, but again, so this thing is like, so this is something that you should have understood this one, right? Minimum spanning tree is on top of the direct, is for the undirected graphs, right? Minimum spanning tree is for undirected graphs, and Dijkstra is something that we can write it for both undirected and directed graphs. So it is no. Simple reason is not because of this reachability issue.
Yes, sir. The concept became clearer last class when we were discussing prims. The idea of why Dijkstra's algorithm might not give the best selection for an MST. Like
yes.
So yeah, it might not choose the minimum weight.
It need not choose the minimum weight.
So it became actually clearer after the last class. We had our minimum spanning tree. Yes, sir. It was clearer after the last class. I would say that.
Yes, sir. Okay. I also got it from the last class.
Okay. Yeah, because I mean, yes, it is true that it is not written in terms of the undirected graph or something like that. Whether directed graphs are directed or undirected, nothing was clearly mentioned there. But I mean, if you had doubt, you could have asked me. But the definition of spanning tree doesn't have any direction, right? So definition of the spanning tree is for the undirected graphs. And Dijkstra is something that, I mean, if you look at our notes also, so Dijkstra is the minimum shortest distance. It doesn't have to be directed. I mean, even undirected also works. And the first example that we did with Dijkstra was for undirected graphs. Yeah. So I think the problem one was from the notes, from the things, right? Problem 3 was also from this stuff, right?
Yes, sir. Problem 1 and 3 were there in the problem set.
Even problem 5, if I'm not wrong.
So problem 5 is a sorting problem, right?
It is not a sorting problem. It's a binary search problem.
Oh, so it's a, but sir, it wasn't featured in the BST, DST problem set.
It was not there. Okay, but anyway, okay, fine. Okay, so I thought that it was there, but maybe I was wrong. But something of this form was there. In this.
There was a problem, sir, which was based on inversions. Not, I mean, it was like we had like the question of like there were n points on two parallel lines, and then we had the intersection kind of thing. It was not quite reducible that way, but
the similar argument will go through. Yeah, and I think the problem 4. Okay, problem 4 is not hard, but I mean, did you get problem 4?
Sir, only sir, I had to be honest, like problem 4, like we have seen as puzzles, like only the 12-point thing. Yeah, I think I have seen it. Like I know of like puzzles, like 9 coin, 9 egg, and 12 egg type discussion, but not like a case where like you're discussing for okay what happens for 13, like that I have not.
Yeah, so but that I mean not everything has to be seen beforehand, right?
Yes. No. So sir, the problem was I thought I would like attempt it afterward. I didn't get like enough time to even think about it. I didn't get like the line of thought like how to proceed. I didn't know.
What about others?
So for me personally, I was able to crack part C, that too only in a few cases, like after spending a lot of time. Part A and part B, I wasn't even able to start. And for part C, for that n equal to 12 case, I was not able to crack it down fully. But you can say like half of the part. Like in some cases, I was able to reduce the things, but not in all the cases.
Okay. So what about so anybody who has tried part A? So nobody could even attempt part A?
So I tried to do something, but I was not able to so I tried to draw a decision tree.
Yeah, good start.
So my first inference was that if I divide all the points into 2 parts and I weight them, and if the parts are equal, then even if the parts are equal, then it would be of no use, because one would be that would be mismatched, but we cannot say which one is in which one. So the thing that I tried to divide them in 3 parts, 3 equal, so and I weight any 2 of them. But the problem that I was facing was that even if I do this, so this is the minimal approach thing that I was going forwards, but I was not able to so I was able to do the A and B, but I was not able to find the third thing.
No, but you could solve the A and B, right?
Yes, sir. I was able to do the A and B.
Okay. Actually, the A and B were the main questions, although we gave same marks for all these 3. But the main reason of this problem was the A and B part. The third part, I agree that it has some amount of trick involved in it. So you have to find a solution. But the A and B actually is actually very simple once you see it actually.
Yes, so if we perform comparison, if we divide into 3 parts and just compare the first 2, if they are equal, then the third part would be the one which has defective one. And we have to do the similar things to do that. And I was not able to prove that this will be the minimal approach. That's the thing.
Oh, so you gave an approach which is more than where
yes, so I think that this would be the minimal because
oh no, but that is not a proof.
Yes, sir. If I just take the 2 things, then
that is not a proof. That is not a proof.
Sir,
Okay, you give an algorithm or
sir,
technique. Yeah.
So if we draw the decision tree, the
Yes.
height of the decision tree is actually the number of comparisons we are making, right? And each leaf represents an outcome.
Exactly.
So if height is h, then there has at most 3 to the power h leaves. And
exactly. So you get only every time you compare, make the first move, right? You can have only 3 possibilities of output, right?
Right.
The next one also you can do. I don't know what you are what all things that you are doing, right? So this is one move, first move. This represents the second move layer, right? And this represents the third move layer, right? And at the end you have leaves. How many leaves will be there?
Sir, there are 2 times, and because like we don't know the way.
Hold on. Number of leaves. Let's count the number of leaves.
Yeah, it is at most 3 to the power h.
3 to the power n, which is 3, right? So for now, let's say just 3 things. It will be 27, right? But
yes.
Output, how many possible outputs? Number of possible answers. How many possible answers? It is 28. It's 2 into 14. Because any of the 14 coins can be there, and it can, any of the coin can be, it can be heavy or light. So it's 28. So you have 27 leaves, 28 possible outputs. How is it possible?
Answer for 13.
For 13, what happens? 13 is slightly more harder. Okay, but 13 is also similar. So I will ask you to go and think about it.
Okay, sir. Wait. Yes, sir.
But basically, this is the main idea.
Sir, this is the trick. Like
this is that. This is the solid. This is the lower bound. See, once again, I mean, if you were using your brains to some level, right? It's the lower bound problem. We have only seen one lower bound technique, which is decision tree, and that's it. I mean, we have not seen that many lower bound ideas, right?
Yes, sir. I think only decision tree we have seen.
Only decision is the only lower bound technique that we have seen. So it is almost like written in there that use decision tree techniques to solve a lower bound. At least the first one was like a trivial thing. Again, as I told you, 4B is just 1 second. Hello?
Yes, sir.
Yeah, sorry.
Yes, sir.
Yeah. So, I mean, this was the 4A. Now, 4B was, again, once you have this idea, 4B is just one more step extra. Okay. Just one more step extra. And 4C is also, the 4C is a different one. It's like the opposite upper bound kind of stuff. But once you see this idea, then also you kind of it's not too hard. I mean, I don't think that you should spend more than 15 minutes on problem 4 to solve this problem. Right. So problem 2. I mean, do you want me to share the screen or something? Maybe we can go over it one by one. Actually, in that case, should I kind of try to share this problem? Just one second. Let me just do that. So, did you guys actually think about the problems afterward?
Yes, sir.
Yes, sir.
So, did you manage to get all of them?
Yes, sir, but not all. I was think this one, the coins one, I was like I wasn't getting it, but now I think it made sense, like very easy. Yes, sir, but I think the Dijkstra tree one, I got from the last class, and also there was a discussion on the medians one, the recursive median.
Yes. Recursive one.
Yeah.
So recursive one, actually, there was an issue in the problem. So I don't want to really go into that. Anyways, we will see. Maybe I will give you extra. I mean, everybody full marks on that.
So it was discussed a little bit in the last class also. So I think most of the problems we got.
Yeah. I mean,
Sir?
let me just go to.
I think. Yes, sir. I'm telling on my
Right. Okay. So first problem I am not discussing because this is something that was done in the problem set. Yeah.
So the problem 8, there is a
mistake. Yes, there's a problem mistake in 8. Yeah.
I tried hard to understand, but I couldn't understand anything for the problem.
I mean, you could not understand anything, or you could not prove it.
I could not understand anything in between the lines. I thought
so
something was missing, and then
no, nothing was missing. I mean, the problem had a mistake, but that doesn't mean that you should not be able to understand the algorithm. There is an algorithm which is well clear. Okay. So maybe I can go over the algorithm, what is there, but the algorithm doesn't do what it's supposed to do. That's a different issue. Okay. So issue was not that there is something missing or something. The algorithm that we wrote is not finding the median.
Okay, so will you discuss a problem 8 today?
I will discuss what?
Sir, problem 8. Sir, am I audible?
Yes, you are audible. I will not discuss anything particularly. I will just go over it just to show you guys what is. I mean, So what all things that I expect you guys to do.
Oh, okay.
Or expected you to do. Okay. So problem 1 was kind of there in the problem set. So problem 2. Okay, so how many of you have done it? This is something important. Hello?
Sir, this is for a directed graph, right?
This is for a directed graph. Yeah, I can think of it directed. But again, you don't have to be a directed or non-directed, right? It's the adjacency list.
Sir?
Yeah.
Right.
So I was able to find the time complexity. So just sorting individual.
Okay, good. So sorting individual is a solution, right?
Yes, sir.
Okay, so this problem has multiple layers. Okay, so as I told here that, I mean, the time complexity, better the time complexity, better you can do, right? So a standard, most trivial one. So basically, what is it saying actually? So what is the kind of a graph? What is the adjacency matrix look like, or adjacency list, right? So it's like the vertex 1, 2, 3, 4, and so on. And from each of them hanging its all the edges, vertices to which it has edges, right? But this one need not be sorted, right?
Yes, sir.
2, 1, maybe just 1, and so on, right? So the idea is that you have to sort each of them. Okay, so you have to sort each of them. That is the problem. Okay, so just to kind of go over it. So we have an input of the adjacency list representation of the tree. Okay, but the list of neighbors is of the vertex vi is not in a sorted form. So these lists are not sorted. Design an efficient algorithm to sort each of the n neighborhood lists. So there are n neighborhood lists, right? So 1 to n, sorry. And you have to sort all of them, right?
Sir,
Yeah.
the way I did it was like create another blank adjacency list at first, and
Okay.
then so since I assume that, so actually I asked in the examination that is the graph directed or not. So you said directed. So
Again, it doesn't matter whether it is directed or not. Okay, tell me your solution and then you'll understand what
yes,
you're doing.
so I mean the directedness is necessary in my, I guess, because so suppose there's a connection from 1 to 3, but this is possible that there's no connection from 3 to 1. So that's
Right.
so suppose so at first therefore I reverse the edges. I mean in case
Okay,
of
yeah.
undirected graph, I guess that was not necessary. So suppose so at first we are in the first we are considering the first vertex 1.
Yes.
So vertex 1. So
Yeah, you reverse the edges and then what do you
reverse the
do?
edges. Then so suppose the first vertex that we can see here in the example that you have mentioned here. So 3 is the first one.
Right.
So we can, so after reversing the edges, we can include in the blank adjacency list that we have just created, we can include 1 in the adjacency list of 3.
Yes. Yeah,
And
you're telling me how to reverse the edges, right?
no, sir. No. I mean,
Okay.
once we have reversed the edges.
How to reverse the edges?
Sir, I mean, I simply wrote that we after reversing the edges.
No, but how do you reverse the edges?
Sir, if 1 is connected to 3, let's say I go to 1, then I see 1, 3. If 1, 3 is connected, then on like 3 in the blank adjacency list, 3 in like 3, I will give a connection 1. Like
perfect.
3.
Exactly.
So I'll read it.
Okay, so you will go to here. Okay,
Oh,
so
yes,
you have
sir.
this 1, 2, 3. So let's try. So if you have just told me just how to reverse the edges, okay, if you just reverse the edges, that is not an algorithm. You have to tell me how to reverse the edges. Okay, so as your friend is saying, so one thing is that okay, go to 1, right? You went to 1 and said okay, in 1 there is an edge 3. Okay, so that means I do is that I instead maybe I can go to, so I look at 3 and I go to 3 and put a 1 here.
Yes, sir.
Right.
Then I go to the next one, go to 2, I put a 1 here.
Yes, sir.
I go to 4, I put a 4 here.
Yes, sir. Parents have
Sorry, yeah. Yeah. Right?
Yes, sir.
Go to. Then I go to 2, right? And in the 2, I look at, okay, there's a 1. So I go to 1, I put a 2 here. Go to 3, I put a 2 and the after that. Go to 4.
So this would be
linear. This will be sorted. This will be sorted.
Exactly. It's sorted.
Yeah, this will be sorted.
So this is, if this is called G, this will be the G reverse. Right? This is an adjacency list. And note that this adjacency list is already sorted.
So don't we need to apply the same algorithm on GR once again?
Yes, you have to do that. That's all that we have to do. You
So
take the G.
How do we come up like this? Like
you go to GR and from GR you go to G. Or GRR basically, which is equals to G.
Yes, sir. That's what we did.
So now how do you come up with this algorithm, right?
Yes, sir. I mean, it
Okay,
looks
so,
simple when you tell it.
Yeah, so that's why I did not ask. Yeah, go ahead.
Sir, at first we will run this algorithm on GR and then again on G.
Then again on GR. So you first run it on G, right? To
Yes,
get GR.
Yes, sir.
How much time does it take? No, I'm going over each of them once, right?
So order M plus N, sir.
Yes, sir.
So this will be order N.
Order A.
Order E
M
plus V. E plus
yes.
V.
Yes, sir.
Yes, sir.
And now you have got this one. And
Yes,
do
sir.
the same thing over here.
But for a directed graph, is it necessary?
Yes. Of course, it is necessary. What do you mean it is not necessary? This algorithm, this graph and this graph, you think is same. In fact, for undirected graph, you can say that this is not necessary. But for directed graph, this is very much necessary.
Oh, okay, sir.
If for undirected graph, just running it once is good enough. For directed graph, it run it twice.
Okay, sir.
For directed graph, so for undirected graph, so this is for undirected. GR is equals to G. But for directed graph, that is not the case. G reverse is not necessary, but G reverse of reverse, this is equals to G. So for directed graph, you have to do it twice. For undirected graph, you have to do it once.
Sir, actually in the examination, I did it 4 times. So, I mean, essentially we get the same answer and the complexity is also same. So, I mean, does it?
Why do you do it 4 times?
Actually, I misunderstood something, I guess, because at first I started with the reversed edges. I mean, the graph with the reversed edges. I applied the algorithm, then I reversed the edges once again, and then applied the algorithm.
Okay, whatever. That's fine. That's maybe a small error. So that is not a problem. Okay.
Sir,
But
I thought the input is undirected graph, and I did just only once.
that's also is fine. Okay. So that's like small things.
Yes,
I'm
sir,
not going
I
to
have
deduct
also
marks for
done
that.
only once. I thought it will be same for the director.
That's okay. That's I will not deduct too much marks on it. Maybe 1 mark or something I'll deduct. Okay. And in fact, there, as somebody pointed out, somebody has told that one can just whatever
Just counting sort.
sort of counting sort. Okay, good. So if you apply counting sort, then each of them, how much time will it take?
So di plus n. Di plus n time. Or
Di plus n. What do you mean?
so sorry, di. Yes, sir.
So it will take di plus v.
Why is it take di plus n?
So n is v, right? Mod v.
I mean, what is the time taken to sort this thing?
So it is di plus v because
it is di. Come on, man. This is how you should be able to say. How much time does it take to sort a list of size di?
So, but if we're doing counting
Sir,
sort,
in counting sort, in range from
okay,
0
counting
to
sort.
k.
Okay, in counting sort, it is di plus n. Okay,
Yes.
that's what you mean.
Yes, sir.
Yes.
Okay, you can do
So
di
in
plus
this
n.
way, if we sum over all the I, then we are getting actually big O of n square.
Okay, good. So, okay, so
Yes,
if you
sir.
do counting sort, you will get di. You get big O of n square.
Yes, I just wrote this one.
You just wrote di plus n.
Yes, so just summing over it and just writing. So I was not able to get the linear thing.
No, you could. That's fine. Again, I'm not going to give you 0 marks for not finding linear thing. I'll give you more than half marks if you can write this whole. This is what summation of di is e, right? Plus n square, right? So this is this.
Yes, sir.
You can do actually much different than that, by the way. Okay, let me give you. I mean, you don't have to reach this. See, this one is linear. Okay, so that is the best. But even if you cannot do linear, and if you just think in this direction, this is actually the weakest thing you can think of in some sense. Okay, so sort each. But in sort each, why are you using counting sort? Sort each using say merge sort. What happened then? This much you should be able to do, right? How much time does it take to sort one of them?
Di log di.
It is
Di
log
di.
right?
Yes, sir.
Now this is over I, right? Now, okay, so now you can do it a lot of things. So one of them way is to say that okay, this log di is just less than log n. So this will become log of n times e. Okay. Now, depending on whether how big is the e, it's not very, or how big is the e, which is better is not very clear.
yes, because the above one can be v squared and this could be v log v.
It can be V log V.
Sorry,
Right?
V squared log V. Like it could be V squared log V.
So this can be V squared. The E can be as small as, I mean, it can be a sparse graph, right?
Right.
So E can be also of the order of V.
It can be of the order of V squared, right?
E can be order of the V squared, but lower bound also. It depends on the E, right?
Yes, sir.
How big is the E?
Yes,
E
Yes,
can,
sir. Yes, yes.
right? Of course, there is somewhere in the middle also, okay, which is the summation of, if you don't use merge sort, but they use simple, say, bubble sort and all. There's this one, summation di square. So there are lots and lots of these things. And this is exactly what I expected you guys to do here. That's why it's written that design an efficient algorithm to sort a, what is the time which can, then of course I have asked you to do a linear time. But see, the fact that it's written the design an efficient algorithm, it means that once you come up with something, you can try to argue other faster algorithms, even if you cannot do linear. Okay, so I would say that if you solve this question, if you write it here, I would give you maybe out of 10, so it was 10 marks or 15 marks, 15 marks, right? So maybe you get, say, 8 marks, something like that. I'm not saying that this is what will happen, but I might give you more marks. And if you get, say, if you can also write this statement that, okay, so there are both of these things, then you get if you write both of them, then you get, say, 10 or 11 marks. Separately, you just write one of them, you get 8 marks. And now if you, of course, solve the linear one, you can do better than that. So basically, see, this algorithm is there and you are asked to solve it. Now, solve it in whatever way you can solve it, and then try to improve it. They are very standard things to be done. Of course, I completely agree that the linear one possibly requires a little bit more creativity. So, but I would have expected you to at least make multiple attempts of this kind of stuff. So same thing for this problem 3, I'm not explaining because again, this was in the problem set. Problem 4, as I told you, it was kind of almost trivial, the first one. It was there. Proves that 3 measurements are not enough. Now, that doesn't mean that I give an algorithm and takes more than 3 measurements. No, that is not. It means that there doesn't exist any procedure that makes 3 measurements. So that's a lower bound. Okay. It is not like, oh, that my quick sort algorithm takes order n squared steps. No. So it can, so fact that no sorting algorithm is there that solves less than n log n is the important thing here. And so this is the first one. The second one is just one more extra case study basically. And the third one is there. Now, fifth one is actually once you have an algorithm and it asks that design an efficient algorithm of runtime order log n. Okay. Now, how many algorithms do you know of that has order log n runtime?
The binary search.
That's the only one that you know.
Yes,
yeah,
only binary search.
Exactly. So it's also written there almost. Use binary search. I mean, that's the kind of the most natural thing. Okay, is there any algorithm that I've seen that uses less than that? So order log n, binary search, flat. Right. This algorithm was actually, problem 6 was possibly the easiest of them. Where, there is nothing actually to be, you have to run the Dijkstra, just think about it. Just go over Dijkstra, what happens there, and that's it.
Sorry, I felt that the C part of this question
Yes.
It's a bit of an elaborate proof. So it was
It is
making,
not a very elaborate proof. Okay. So, I mean, the main idea is that there are, I mean, so here is the graph, here is S. Some of the edges going out of it can be negative,
right.
right? But there is no path back to S.
So if we are writing a proof, then do we have to use all the U, V, V1, V2, dot, dot, dot? So if we can show it like a graph, like a small diagram and explain.
No, that's not good.
Okay, sir.
No, I mean, you are a mathematics student. You should understand that.
So that's why it was taking a bit long to write this
And
question.
you have seen Dijkstra. It's like writing I mean, how much long can it take to write a proof of Dijkstra? I mean, don't tell me that that took you 1 hour to write the Dijkstra proof.
So it didn't take 1 hour, but it was actually, since it's like trying to explain rigorously what the proof of correctness for Dijkstra. It is almost a replication of Dijkstra.
You just have to replicate the proof of Dijkstra. That's it.
Right. So, but then when we're trying to explain it in words and then we're trying to write it down rigorously, I felt it was a bit elaborate. Maybe I did a very complicated technique. So actually, what I was trying to say was it felt as complicated as a 15 marker in some sense. So could you perhaps revise the distribution of the marks here? If
I don't think so. First of all, I don't think this is a 15 marks thing, period. Okay. I mean, Dijkstra's algorithm, you also know the proof technique, right?
Right.
You guys have been asked to go and read stuff, right? So of course, Dijkstra's algorithm proof was done in class. There are the books there, any number of books and all. You are expected to know that, right? To some level.
Okay.
I mean, come on. I mean, this is not something. I mean, the only thing that to be done is that you have to really think about these negative things, negative edges, whatever is happening here.
Right.
So it's a recursive algorithm, right? Not recursive, sorry. I mean, it's a step-by-step algorithm. You prove it by induction, right? I mean, that's the main idea of Dijkstra. That at any point of time, if T of them has been given, so if a set of vertices have been marked red, right? And so these are the vertices for which we already know the shortest path. Then if I look at all the other vertices just outside this set, and if I take the vertex which has the smallest number for here, then this is the shortest path. And the only thing is that, okay, if it is not, so if this is a particular distance D, this is W, can there be another path outside, longer path outside possibly, that has a lower cost than this? That is the only thing. There's only one theorem there, basically, or one lemma, in fact.
So actually, that is where the complication came up, because then we have to introduce something which is like a distance function in terms of the algorithm. And then there's a true distance function, which is the actual distance from the source vertex, right?
Right.
So we have to somehow give some inequalities amongst them and then try to prove that the distance function obtained by this algorithm is the same as the actual distance function.
Yes.
And that was a bit of there was some work involved. I'm not sure if there was a cleverer way to do it, but I felt there was a bit more work than 5 marks. So that is why I was saying that. But okay, I might be wrong.
Yeah, I mean, I'm not with you in this thing.
Right. Okay.
Yeah. Okay.
Okay.
And what was this one? So this one, number 7. So number 7 was again. I mean, it's again. It had, once you have this log n thing, right? you kind of know that what to apply. Right? It's a binary search. Right? Or binary search kind of stuff like that.
So
Or,
in this,
actually, it is not binary search. Sorry, it's not binary search. But this is something like binary search. It's the recursive version of the binary search.
So is a sort of merge sort.
Merge, yes, sir, like dividing.
I mean, it's the recursive version.
Yes.
Right. It's the recursive version of the merge sort, recursive version of the binary search, whatever you want to say. The recursive version is binary search basically. You start with some two sets, and you keep on. I mean, you throw away some things, right? Every time you reduce the A and B thing, A and B by half. Right. So again, this is something that how many of you got it or not? Did not get it?
Will you kindly explain?
Okay. Yeah. So you have this. So you have this two sorted list, right? A and B, and you have to find out the median of these two. Okay. So what is the first thing you should do? Okay. Maybe the first natural thing is what is the median of this? So let's call this a median of this is X, median of this is Y. Right? So what does it mean? Let's think of it. What does the median means? So there's this now. So median in X means, okay, that half of them are less than X, half of them are more than X. Similarly, Y, half of them are less than Y, half of them are more than Y. Correct?
Yes.
Good. Just 1 second. Hello. Yeah. Are you there?
Yes, sir.
Yes,
Yeah.
sir.
So say what happens. So I have these two things, X and Y. Now let's compare them. What happens in this case when X is equal or X is say less than Y or less than or equal to Y? What happens? Where is the median? So median is somewhere, right?
It cannot be on the right side of Y. That's it.
It cannot be on the right side of Y.
Yes, sir, and it cannot be on the left side of X.
Very good. It cannot be on the right side of Y, cannot be on the left side of X. So that means this chunk and this chunk, both of them are junk for me. They have how many elements are there here? The same element, by the way, right? So say K or N by 2 kind of stuff, right? So if I have a set, right? If I have a big set, the huge set, A union B, this is the median I am looking for. I don't know what is the median. But I somehow magically managed to throw away, say, some 4 elements from here and 4 elements from here. Then the remaining set, what happens to the median?
It will, if we are throwing the same number, then Z will remain the median.
Same thing, right?
Yes, sir.
That's exactly what you do here. You throw away this half, throw away this half. Okay. So now that means A prime equals to A minus everything less than X. B prime equals to B minus everything more than Y. Note that size of A prime is equal to size of B prime. same thing. The same amount of things are thrown, and therefore the median of A union B is same as median of A prime union B prime. So what do? So initially, if I had been calling it as median A comma B, all you do is that in that case you call the median A prime B prime. This is in this setting. The same thing is true for the other case where X is more than or equal to Y. The issue is that running time, I started with two strings, two arrays of size n each, and after one round, one step, right? I have taken n by 2 is the size. So every time the size of A union B or whatever this set union of the two sets that I have given is shrinking by half, by a factor of half. So after log n steps, it will be done. So the total number of round is log n. Is this argument clear? I mean, I did not give you the formal proof of it, but if you want, I can just write it down.
Yes, sir.
It's clear, sir.
I mean, it's just a recursive thing that you do, right? I mean, again, I gave the proof as well as this whole thing together.
So the only thing that might need to be added is the fact that X is lesser than equal to Z is lesser than equal to Y, right?
X is lesser than equal to Z is lesser than equal to Y.
Because then we want to show that the number of elements removed from
no, all you have to show is that, okay, the only thing that I have not shown is something that I think one of your friend kind of told, that if this is the case, then the median is not on less than X. So median is between X and Y. That's also
right.
all you need to show.
Right.
Okay, so then this implies X is less than equal to Z is less than equal to Y.
Right. And this is needed so that we can claim that we're removing equal number of elements from the left of Z and to the right of Z.
Right.
Right.
But this is a mathematics proof. I mean, you go and prove it.
Right.
Sir, I wrote this idea approximately. I mean, I did
That's
not
fine.
go for any rigorous kind of thing.
You don't know, right? What?
So, I mean, I did not go into any rigorous kind of proof.
No, that's okay. That's okay. That's okay. I mean, I'm not hell bent on the rigorous kind of stuff. Okay. I mean, you first of all, maybe I will deduct 1 or 2 marks, but not more than that. If I don't find your things rigorous enough or something. But I mean, more importantly, it's important that you have designed the algorithm and convert the algorithm by step.
Okay, sir. Okay.
So in that respect, I don't. So okay, problem 8, forget that. But rest of them, I really believe this solves this. I mean, with a little bit of smartness, you could have done it, all of them, in 3-hour time. I mean, 2 of the problems were previously known almost. Dijkstra's algorithm was, I mean, there's nothing much to think in some sense. It was just going through the whole thing. Maybe you have to prove it or something, but you don't have to creatively find it. The creative component was maybe in this 4, 5, 7, and in problem 2. So there are 4 problems that report creativity, and problems which were like. So anyway, so this is where we are. So. So one thing that I can ask you guys to do is that if you guys are interested, is that you guys can. I don't know whether that will be a very great idea or not, but I mean, take this them only as an assignment and try to solve it and give it to me once again. So see, so that you also understand. Yeah, I mean, now that you have enough time and you have also seen the proofs or something. So what's going on there?
Okay.
So I will just maybe post it accordingly. I'll also edit the the median thing, which is the mistake here. Yeah. So
So could I just say something?
yeah.
I just wanted to say that actually during an exam setting, it was a bit hard personally to crack those creative questions, and it was taking perhaps a bit too long to think about some
No,
of
I
them.
understand that. That is always the case. Okay.
Right.
And that is, I'm not saying that like everybody would be able to solve it in 3 hours sometime or something like that. I'm not, and I don't personally believe in giving too long things. Okay. But I'm just saying that it is, I don't think it is too long. I mean, I have not corrected the papers, but if you had been a bit more, trying to finding out clues, like, whenever you have a login, that means it's a binary search. Whenever you lower bound, that's a decision tree, lower bound. So this kind of clues that you start getting it,
right,
you could have done a better job possibly.
Okay. So actually, even though we've solved all the problem sets, perhaps we were lacking a bit of practice. At least, okay, I should say personally. So, what exactly should we do in such a situation? Because I felt I was well practiced with at least all the problem sets, but I still was struggling during this exam.
Yeah, see, again, as I told you, the only solution is to practice. Okay. Now, of course, there are these books that you can take. Okay. The one thing that happens with the problem set is that is something that you already know, is that once you give a problem set, right, you know that this problem set is mostly coming from or solving problems using techniques of the last week.
Right.
And that is something very useful to have when you try to solve it. But in an exam, there's nothing like that.
Right.
Right. So I've given you a problem, but that doesn't mean that that problem is coming from, that can be solved by binary search or by recursive algorithm.
Right.
Okay. So that is there. So we can give you more and more problems. There's no question about that. But also, there are the books. Okay, there are very well standard books in algorithms. So please go over it. Try to solve some problems there.
All right. Okay.
Yeah, I must say that since it was your first proper exam in algorithmic thinking and all those things, I'll not be too harsh on you in the sense that, okay, you should have done it or something, because this is something that you possibly have not, this kind of thinking you have not encountered that much till now before this course, right?
Right.
And so it will take some time before you start thinking in that direction. That's the only that's basically the main goal of this whole course, to think of any problem in an algorithmic way.
Right.
Okay. Yeah.
Okay.
Yeah. Okay. So, any other questions, comments? Some other suggestions? Anything is fine. I'm up for anything.
Sir, if I may suggest, probably this is my own problem, but I think a change in the format of the answer should also help, because writing the algorithm, then the proof of correctness, then the time complexity for each such problem that demands one is very time consuming, especially in an exam.
Okay. If you want to, I'm not saying that you have to do it in that way. Okay. Sometimes myself only, when I write it, I kind of tend to combine some of these stuffs.
Right.
Okay. Which is, again, I am not really, so as I told you, you have to give me the problem, give me the algorithm, and convince me that it is correct. Right. So, that is up to you how you do it. Okay, so like, so if you want to do the time complexity as well as the proof of correctness together, perfectly fine. Or if you kind of design the algorithm while every step you kind of give some argument about why you are doing it, that also is fine. I mean, I mean, basically these are the three parts you have to give me. Now, how you give me, I'm not saying it. You have to give me an algorithm, you have to prove correctness, you have to analyze your time complexity.
Okay.
So in the assignment, I didn't wrote the time complex proof of correctness explicitly. So there was one question where basically we were doing DFS and the algorithm says that it stops at a time when a certain vertex is we have found certain vertex and there is a cycle using that vertex. So I didn't see that how. So the correctness was pretty apparent.
Obvious. No, that's fine. Then don't have to give me.
Yes, sir. In the assignment I wrote that correctness was. I thought the correctness was pretty obvious, but I mean.
So somebody so the TA deducted some marks.
Yeah. So I mean, so she. I mean
that you can have a discussion with her, okay, and try to convince her that is. I mean, if she has some point, then she will tell you, and if you think that no, that is obvious, then that's fine. I mean, that I think that details.
Yes, sir. I think I also faced it, but I had a talk and I think it got resolved.
Yeah, I think that is fine. So this is like a standard step jump thing, right?
Yes, sir, because it was already mentioned in one of the tutorials that whatever is done in the class, let's say DFS, that can be taken as a black box.
Yes, yes, that can be taken as a black box.
Sir.
Yeah. Yeah.
Sir, and in the beginning of this course, you took a class test, and in the class test there was a problem on some graph problem on some siblings, right? So, sir, I just wanted to ask whether this sibling relation is transitive or not. So, if A and B are siblings and B and C are siblings, then can we say that A and C are siblings? So, because I think this is a transitive relation, right?
Yeah.
So I was told that it is not. I mean, so I used this fact that since the relations are transitive, so I formulated this as a graph problem. And so if so I was considering like a group, like groups of siblings. So all those groups of siblings will make complete graphs, disjoint complete graphs. I argued in that way, but I was told that no. So this relation of
so it is about the assignment 1, is it, or the quiz 1?
It's that quiz 1, yeah.
Okay, so I don't remember the problem at all, and let's take that discussion a bit out. I mean, that's a different thing. I mean, this I think will kind of take. We can have a. I mean, why don't you chat with the TAs, and if you are not convinced with whatever they are saying, then you can.
Yes, sir. Actually, sir, I chatted with her, but I mean, she said that the relation called sibling is not transitive.
I mean, relation of sibling is transitive unless you are talking about some other.
Yes, I mean that's what I told. I mean that's what I used in the problem. So, sir, in that case, what?
Okay. Why don't you send a mail maybe to me, and maybe or we can have a discussion on that. So anybody else of you, rest of you have some similar problems as he is pointing out about this problem, sibling problem?
Sir, that same question, I also had a problem, but I didn't ask her what the problem was exactly. She told to think about it yourself. So,
okay. I personally don't even remember what was the question. So let's. Yeah. Anyway, that is. Okay, we can take that one off separately. Okay, so let's go. Okay. Any other points, questions? So okay, so we have very short time today left. I mean, I started also half an hour later, but so today, whatever time that I have, what I will do is that I will. So we have seen where are we right now? Okay, we started with this algorithmic way of thinking. We did some problems in algorithms, kind of in a random way. We started with binary search, researching. We did sorting. Then we did some kind of some graph algorithms like DFS, BFS. Then we did some the shortest path problems, right? Then what else did we do?
So all part.
Yes, so sort of yeah,
APSP.
yeah. So single source shortest path and all pair shortest path, right?
Yes, sir. And then next class,
So then minimum
minimum
spanning
spanning.
tree.
You have done minimum spanning tree, right? So we have been kind of all over the place. We are just, so this first half of this course was used to mostly to kind of get ourselves, familiarize ourselves to this algorithmic way of thinking. Okay, so in this thing, maybe you have seen that we have used different algorithmic techniques at different times, which you have not exactly in your head possibly managed to divide them in a nice compartment of what kind of algorithms are going on. Okay. So, so let me kind of tell now that there are many. So these algorithms are not just all of them are not say ad hoc techniques that you come up with. So in fact, there are 3 main techniques that are used. Okay, actually, I mean, there are many techniques, but for your purpose, for the purpose of this course, you can think of it. So there are 3 main algorithmic techniques. You have seen almost all of them to some way. The first one is what is called as greedy algorithm. So what is greedy algorithm? So greedy algorithm is you start and try to do something just to optimize, I mean, just to do it. For example, in the case of sorting, you guys remember we had done this, say, bubble sort, right? Or selection sort. Now these were like greedy algorithm. Meaning, okay, I want to solve it. I have to sort this string, sort this array. Okay, what is the first, what is the smallest element? Let me go and find it out. Then what is the second smallest element? Let me go and find out. So I'm doing it greedily. Okay. Another example of this one is, say, in some sense, you can think of is, so in the last class, you have done this minimum spanning tree, right? The Prim's algorithm. So you want to find out the minimum spanning tree? Okay, let's pick up the minimum edge weight and let's pick it. And then what is the next minimum edge weight? Then pick it, and so on and so forth. Right?
Sir, would that still be a greedy algorithm? Because what we're doing is we're providing it a bit of a structure, right?
We are not doing that much of a structure. We are seeing whether the cycle is formed or not.
Okay, right.
And if cycle is not formed, we just continue. Right.
Oh, okay, right.
So these are the examples of greedy algorithm. Okay. Now with greedy algorithm, the issue is that there are 2 issues. Number one, okay, so what is the advantages of it? They seem to be the most simple form of algorithms. Okay, do something. Okay, do whatever you want to do, kind of stuff. But the problem is that even its correctness is not very clear. Correctness is question mark. It is exactly something that you have possibly seen in many, you have not seen possibly. So in many other techniques, like for example, in, so what do you call, say, gradient descent or finding the minimum of a function, and there are lots of various problems that you will face in both in statistics or optimizations and so on. Okay, where this same problem comes in. Okay, in fact, I will give you a very nice example of this greedy algorithm, which comes from this machine learning area, and something that has been very that has been there for quite some time. I mean, it was designed in the 1940s or 1950s, and finally the correctness of the algorithm was proved in 1980s. It's a beautiful algorithm. So that is something that I will do maybe in the next class or something. But the main issue is that the algorithms are simple, algorithms are easy to design, but the correctness of the algorithm is very hard to prove. Now there is a second category of algorithms.
Sir?
Yeah.
Sir, I just wanted to comment on this. So if we were to look at an algorithm, we would talk about its correctness with respect to trying to solve a certain problem, right?
Yes,
so,
and I'm not talking about in terms of running time. I'm just trying to solve it in terms whether it actually solves it in, yeah.
Right. So something like if we look at the greedy coloring algorithm in graph theory,
right,
which is whether we can achieve a coloring with
right,
some number of
right,
colors. So if the problem was to color it in the minimum number of colors, then its proof of correctness, I mean, we can prove it to be incorrect.
Exactly.
And if it was just to color it in n colors, I think, which is
some colors, some number of colors, somehow give me a coloring, yes, that will do it.
Right, the minimum degree, I think, is what it says. Then it will be provable. So there we have to redefine maybe the task itself that it's trying to achieve.
Yeah, the task is to find the minimum in the case of the coloring, right?
Right.
So there are two parts of it, right? Task is to find the coloring. Of course, the task is to come up with a better, smart algorithm, meaning a fast algorithm. I'm not talking about the fastness. I'm not worried about the runtime. But even the correctness of the algorithm is not very clear.
Okay.
Like the Prim's algorithm does something, but at the end of the day, why does it actually output a minimum spanning tree?
We require the cut property to prove that.
You need a proof, right? That's all.
Right.
And that is by no means obvious. Right. So these are not as obvious that you are saying that okay, this many of the algorithms that you are saying, oh, we have the obvious, this algorithm is obvious, then why to write a formal proof of it? Right. I understand for many of them, but for these things, that is not the case. For MST, this is not the case. Right. In some sense, sometimes you can also put Dijkstras over there to some level. Dijkstra is also a kind of a greedy algorithm.
Yes.
Okay. The second one technique that is have, we have the recursive algorithms. And the recursive algorithms are very neat, and it is kind of the proof of correctness are kind of not necessary to be done that much. Oh, by the way, I forgot. So I wanted to talk about problem 8. Sorry, I will do that. So the recursive algorithm, so for example, the merge sort, the quick sort, right? In fact, we have seen the recursive algorithm even for talking about the all pair shortest path kind of stuff like that, right? To some level, it is kind of repeated doubling, the doubling algorithm.
So the repeated squares.
So repeated squaring algorithms, yes.
Right. Okay.
So here the main idea is that here in this setting, the main idea, what is hard, is to designing is hard. Designing is hard. Now, hard in the sense that it requires you to think of how to break the problem into smaller parts. Okay.
Yes.
And once you break the problem into smaller parts, then you have the recursion that is there. The algorithm, even if I ask you to kind of possibly write a code, it's a very trivial code that comes up most of the time. So it's just something that we just now did before, like the median of these two sorted lists, right? Once you kind of know how to break it, right, the proof is already here. The proof and the designing kind of goes hand in hand here. Okay, and the runtime. So runtime is actually much easier to analyze. It's easy because it's a recursion again. So the main idea here is how do you break it, right?
So and also these are not very hard classifications, right? There are some gray areas where we would.
No, they're not. None of them are hard classifications. No, I'm not. I mean, I'm just telling you because you will feel many of the books tend to classify problems in this way.
Right.
Okay, so these are like, let's do a greedy algorithm, let's do a recursive algorithm.
Okay.
In some sense, you understand what's going on there. You should not get blown away by reading it. That what's the greedy algorithm?
So they're more like paradigms or schools.
In some sense, it's like a paradigm. Yeah.
Right. Because I feel Dijkstra can be somewhere in the gray area between these two things.
Exactly. Right? Dijkstra has a bit of a recursive concept in it.
Right.
Right. And the third one that you have kind of already seen to some level, and we will see it more in the next in this next week or something, is dynamic programming. Now dynamic programming is like recursion. Okay, so like what are the examples of dynamic programming? This Floyd Warshall. And the Bellman Ford. So here the idea is that you tend to design, so these are recursive algorithms, but you have lots of the sub problems comes again and again. Okay, sub problems reappear many times. Okay. And since the subproblem reappears, the whole idea is this very basic stuff that just saves the calculations or computations in some sense. So once you save the calculations or store these calculations in some nice way, then you can reuse it as and when is required. And that saves a huge amount. So in some sense, the recursive and the dynamic algorithms are kind of goes hand to hand. It's not too different. Okay? But this main difference is in the recursive algorithm, you are not storing information in some way. Okay, you are just calling a smaller problem straight away. So something like here, right? You want to compute median of AB, you do something, you compute A prime, B prime, and say, okay, go and output median of A prime, B prime. That's it, done. So we don't have a global array or matrix where things are stored. In the case of dynamic programming, it's a recursion. You kind of split up into small parts and all of that, smaller problems. But this thing is that the sub-problems, you kind of store it. So you kind of break it down to small parts and rebuild the whole thing from there.
So it's more of an optimization of recursion in that sense, right? It's like
in some sense you can say that, yeah.
In an ideal world, what we would want to do is, if we want to build up to a dynamic programming, we want to firstly think about a recursion, and
Right.
then we want to identify what sub problems are reappearing, and then how we can
Right.
think about storing them from the beginning.
Right.
Right.
Okay. So this is what the three classes of algorithms that are there. So what we will do in the next few this week and next week is that we will look at some of the some classical cases in the case of, we have already seen, so something in the set of greedy, something in set of recursive, and something in set of dynamic. So dynamic, I think we will spend a bit more time, something that we have not done. And after that, we will move on to another important algorithmic technique that we will come after that.
Sir, I had a question.
Yeah.
Sir, the three techniques.
Yeah.
Given a problem, is it like a problem can be solved like by either of them?
No, it doesn't matter. It I mean,
what I'm trying to ask is it theoretically possible that a question is solvable by all the three techniques? So its only thing is which one is a more cleaner and a more appropriate implementation, like, or a much faster implementation. I don't know. So that what I wanted to ask is that, like, knowing these, given any problem, like, is it possible to know that knowledge is the knowledge that it is possible to solve it using any three? Like
kind of true. Like, for example, this Belmont Ford, right? I mean, so we have this repeated squaring algorithm.
Okay.
That's a recursive algorithm. We can improve it to Bellman-Ford. That is a recursive, that is a dynamic programming algorithm. And you can think of it that all of it, instead of doing this thing, you can do it with Dijkstra's algorithm, which is a greedy algorithm. So the same problem, we can solve it in three different ways. Yes. So, I mean, it's not necessarily the case, but many times it can happen. Or sorting, right? Sorting is a good example. Sorting is a good example where you can have selection sort and so on, which are greedy algorithms, and you can have merge sort, which is a recursive algorithm. Right. So that kind of, so by the greedy algorithm, in some sense, you can say that there are always greedy algorithms in the world. Okay. Now, of course, it's the optimization thing that comes up there. So there will be some trivial greedy algorithms which takes exponential amount of time and so on. Okay. But that's not, yeah. So, but the main idea that we are saying is that there can be greedy algorithms which are also fast in many sense. Okay, so how much time do I have today? Okay, I have 10 more minutes, or maybe I can take some more time, but that's fine. So let me jump to areas and let's talk about a problem in machine learning. How many of you are interested in machine learning? None of you?
Sir,
No, sir. I think a lot of us would be.
A lot of you? Okay. Good.
Yes, sir.
So what do you think of machine learning? What is machine learning?
Sir, it's basically solving like some kind of a classification. Right?
Okay, classification is one form of it. That's good. So basically, you have a function you learn. Okay, that's the basic idea.
Yes, a classifier, some kind of a classifier.
Some kind of a, yeah, classifier is one of them.
So can we say that machine learning is nothing but like future prediction using previous data, most of the times?
Prediction is also a part of it. Okay, it's all about the function that you're learning. So you have a function from a domain to a range. Okay, and you want to learn it. Okay, so what is classification? So for example, say I want to teach a machine that I will give it a to say I will teach the machine to distinguish between a cat and a dog. Okay, I'll give it a picture. Okay, so the domain is a set of photos in some sense of cats and or dogs, and it outputs either +1 or -1, or meaning either it outputs from to the set a dog or a cat. All it has to do is that it is take a photo and just say that it's a dog or a cat. So this is the binary classification. It gives a photo, it outputs it. Okay, you can have, you want to learn or teach a machine how to learn handwriting. Okay, so I will write a number. Okay, and it has to look at it and tell it whether it is number is 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. Okay, so you have to learn the digits. So it's a bigger classification. So classification is one of the problems. I can have different ones. Okay, it can have the data can be our range can be something completely else, different, right? As you say that it can be trying to learn or say, so you guys in your statistics you have to do regression, right? So regression is kind of a, you think of regression is a learning algorithm. It fits the data, it fits the line, and it kind of tries to say, okay, so that means if you now give you an x, I can kind of predict it what and y will be close to it, or what the f of x will be.
Sir, in a sense, isn't it like parametric inference? Because what we have is
Yes.
we already fixed a family of distributions.
Right.
In most cases, it's like for something like deep learning, it's some sort of a linear function family, and there are some other functions attached to it.
Yeah.
But what it's doing is it's implicitly defining a family of distributions, and then we are trying to find out the values of the parameters which fit the data.
We don't really know that which distribution is the data coming from, right?
Yes, we don't know.
So if you have no idea about anything, okay, then there is theoretical proof saying that you cannot do anything. Okay.
So we do assume a set of.
So the most idea that says that you have a concept class.
Right. Okay.
A concept class is basically, I mean, I'm going to talk everything from the point of view of functions. You can think of a distribution as also a function. Okay. Distribution is a huge function in whatever way you think of it. So concept class is what? It's a subset. You can think of it as the subfunctions that you want to learn. So subset of functions. Sorry, can you hear me?
Yes, sir.
Yes.
It got disconnected for a.
Yeah. So it's a subset of functions such that the guarantee is that the given function or the function that I want to learn, that function f, is from that subset. So suppose I have given you a data and I told you that see this data is, so I have said, for example, I have given, okay, so this is something, right? So I've given you a function and say I tell you, say, for example, I guarantee that f is a polynomial of degree 5. So this is a concept class. Polynomial of degree 5 is a concept class. Now you don't know what f is, so the data is given. Now how is the data given? You are given x comma f of x. Now I don't want to be too much into it. It's okay. So you have a collection of f comma x of x, where x's are then there are various ways. Okay, X are somehow drawn. Either they are drawn uniform randomly from some distribution, or they are queried or something of that form. Okay, X are from the domain D in some form. So you have been given, this is the set of input you can think of, or the learning. So you want to learn it. So this is the input that has been given. So you have been given two informations. You have been given the information that a function is coming from the concept class. It's not the arbitrary function. It is coming from some concept class, and that concept class also you know. Function, say, is a polynomial of degree 5. The function has been given in some information. Okay. Now, question is that learn f. Okay. Now, what does learn f means? Okay, learn f means that okay, there might be many functions that fits this data. There are many functions that are fits this data and a polynomial of degree 5. So you have to output something, and the hope is that you kind of want to say that okay, the error term is I will output something. So I will output something, say called f tilde, and the question is that you want to minimize say some kind of a distance between f and f tilde under some distance parameter. So this is basic idea of machine learning. Is this clear?
Yes, sir. So,
Yeah.
so in this case, the concept class is essentially parameterizing of the whole set of functions that we can talk about, right? And in this case, it's e to the power 6 kind of parameterization.
Yes. Yeah.
Right.
Right. Good. So let's start with the most, or maybe not start. I mean, this is not a machine learning course, so I will give you one of the most trivial one. Okay, so I started with telling you about this problem, cats and dogs and all those things. Okay, so how is it done? Okay, so I can look at a picture and I can say that okay, picture is nothing but a point in a huge space. Okay, how can I think of it? So maybe the picture is a, say,
matrix.
It's some pixels, right? They have lots
Yes.
of pixels. They have some k cross l pixels.
Hmm.
So I can think of it as just as then each pixel has some kind of a gray and white is kind of, or maybe you can think of it as not as this plus minus one. Sorry, it has a kind of a. So think of it. It's a black and white picture. Okay, so it has a range of how dark is that pixel, right? So it's r to the power k cross l. That's all, right? So every picture I can think of it as nothing but a huge, is a point, is a vector, is a point in the n-dimensional space, right? And now say, what do I want? So I have the dogs, okay? So a dog will, so if I have a huge n-dimensional space, so this is an n-dimensional space, and of course I cannot draw an n-dimensional space, right? So the set of, let's look at all the points that correspond to this picture of dog. Okay, so maybe I will put it pluses here in some sense. Okay, and if I look at this set of cats, so those pictures are maybe, so these are negative, this is positive. They are some kind of a.
So these pluses and minuses are from the input, no?
They are the input. They are the what's called the labeled thing. Okay, so you have kind of, I have taken lots and lots of pictures of dogs and cats.
Okay, sir.
Okay, now every picture is a pointing in some n-dimensional space, right? And okay, so this is a picture, this point corresponds to a picture of a dog, and this is sitting here. This is the picture of a dog and sitting here. This is a picture of a cat and sitting here, and so on. Okay. And the main idea is that, okay, maybe what I need, okay, so this is something, this what is concept class. I can say that, see, maybe these two sets can be separated by a linear hyperplane. So the idea is that, okay, see, I think if you want to learn it, there is a function where there's a huge linear hyperplane somewhere there. And the idea is that if I get a, if you give me a picture and you guarantee me that this picture is either of a dog or a cat, right? I will look at it as a vector space in this whole thing. And you say, okay, what is this? So, okay, this picture is on this side of the hyperplane. So this must be a cat. So here I'm assuming a various few things. Okay. So number one is that there's a set of dogs and set of cats. If I embed it, or if I look at it as n-dimensional points or points in n-dimensional space, then the set of dogs and set of cats can be partitioned or can be separated by a linear hyperplane. Okay, so that is the concept class. Now, question is that how do you learn the linear hyperplane? So let me just tell you what is it in some sense this problem comes down to. So what has been given? What is the input? Inputs are basically a number of points. Okay. So number of points in R to the power n cross plus 1 minus. Okay. Okay. So that's so inputs are basically x1 to xm. All of them are in this set. So there are points in the n-dimensional space, and each of the points have been marked +1 and -1. Okay, such that, okay, there's a guarantee. So this is a guarantee. Okay, you can think of it as a guarantee that is there. What is it? There exists a hyperplane. Are you sure? So do you know what a hyperplane is?
Yes, sir.
Yes, sir.
So how do you define a hyperplane?
Sir, alpha prime dot x minus like you have equation, right? Alpha prime dot x minus.
So in hyperplanes, can I define a okay? So maybe the best way is that, can you kind of tell me? So if this is a hyperplane, how do you define this space on this side of this side? What is this side?
So one will be positive, sir. One will be negative.
Positive two in terms of what? Okay, maybe I think you're writing, answering the correct things, but just that I'm not getting the right answer. So basically, if you look at if you
substitute these points, yes,
look at the perpendicular. So let's call this perpendicular be star theta, right? Okay. Okay. So there exists a theta star. Now theta star is also a kind of a point, the vector point, right? In R to the power n, such that, okay. So maybe I should write this one as, maybe I should write this thing as say x1 to xn. Okay, so let me write it just this one. Okay, x1 y1, x2 y2, and so on and so forth. Where xi's are from R to the power n and yi's are +1 or -1. Sorry, +1, plus or minus. Okay, so okay, such that what? That if that yi, let me see, yi is minus or plus, say, if and only if xi dot this theta star is positive. Right. So this is a guarantee that has been given to us.
Sure. So we're only considering the set of hyperplanes which pass
Yes, so
through
it's
the
passed
origin.
through the origin. Let's say we look at all the hyperplanes that pass through the origin.
Okay. Because in the other general case, we just have to replace 0 with another.
Yeah. So let's think of this one. Okay.
Okay.
Yeah. It's a very simple case. Okay. So I have been given this set of points, and I've guaranteed you that there exists a hyperplane that passes through the origin that satisfies this. Okay. Now, my goal is to, what is the goal? Okay, so what is our goal? Find theta. See, there are a lot of, there can be many theta primes, right? Theta starts rather, right? Because I mean, if I change it a little bit, it's not very clear whether that will have any problem. Right? So find the theta such that the above thing holds. Xi equals to +1 if and only if xi dot theta is more than 0. So this is our problem. This is basically called the binary classification problem. And in fact, this is in some sense the first problem in machine learning one can think of. Or linear, sorry, this is linear binary, so linear classifier. Linear binary classification problem. Okay. And this problem is actually very old. This is possibly the first problem. And this problem's importance of this problem comes in the fact that this was can you guess that which group of scientists actually came up with this problem? You surprised this?
Yeah, neuroscientists.
Yeah, this was done by the neuroscientist. Okay, and they also came up with an algorithm. We will talk about that algorithm. Okay, so the algorithm's name is called perceptron, and they gave a what to say, a very greedy algorithm kind of stuff for this problem. An algorithm that was not even clear that why it will stop also, for that matter. But so turns out it is actually a correct algorithm, and it took us quite some time to actually prove it. Okay. So I want you guys to go back and think about this problem. So I believe that you guys should not require too much motivations for this thing, because this is actually coming from a actual machine learning kind of problem like that. And as a data kind of stuff, think of it this way, that this is something that you have a collection of pluses and minuses in n-dimensional space, and all that you have to do is find a separator going through the origin that separates these 2 points, these 2 sets. How easy is it? Okay. Is this problem clear?
Yes.
Yes, sir. Yes.
Sure.
Yes.
Yes, sir.
So we've actually looked at a problem in parametric inference, which was suggesting a solution to a certain
something like this.
Right.
Yeah, I mean, again, this is a very classic setting. Okay, very classic setting. This is yeah, this problem and the solution and everything are very, very classic. So this is
right. So in parametric inference, we just gave a, I mean, I don't know whether that could be called an ML algorithm, because it was just a matter of I think finding an MLE estimate for something or something like that. But then I think that's just another posing of the same problem then.
that same thing. Okay,
So it was just a logistic regression.
Right.
Yeah, I mean, whatever it is, okay, whatever, when you do logistic regression and whatever stuff, okay, at the end of the day, there's two ways of doing it. Okay, one is to apply a tool. Some package is there, you run it and done. Okay. Or in the world of the theoreticians kind of stuff, okay, there is something that you can do. You can come up with this thing. So there are three ways of doing it. One is that a theoretician will say that, okay, I mean, there is such a linear classifier, or there is a logistic regression technique that will output, that will do it, and let's move on with it. An applied person will say that, okay, who cares? I have a tool, I have a software, I input it in, and it outputs me the classifier or the regression values and all. Done. But from an algorithmic point of view, you try to put yourself in the shoes of the first person who designed or developed the software to do the logistic regression. Put yourself in the shoes of the first person who designed the binary classification. Okay. I mean, of course, these are all standard things. So it's like, okay, if somebody has designed, why do I have to design it? But this, we are just trying to kind of increase our muscle power, right? At some point of time, we might have to do something similar for some problem that is not known to us.
Right. So there's a big step here that we jump from such a linear classification problem to a logistic model. So we want to be able to appreciate why that was needed in the first place.
Right.
What were the more primitive methods that we could
What are the most primitive methods, or even the simpler problems and so on, right?
Right.
So here I am asking you, see, that's a guarantee, there exists a classifier.
Right.
Okay. And now if you are pretty much not interested in it, I know that there are very nice packages that you send it, give any data and will output it. But I am asking that what is going on inside the packages?
Right.
What is the algorithm?
They'll be just turning this line. It will still be a numerical algorithm only. Like it will still take any initial configuration and try to reach the final, right?
Yes.
So in some sense, like a numerical approach is what is right? Like even in logic regression, when we are what we are doing is we are framing a model and then to solve it, like in the ML, like for the ML case, we are like trying to use either Newton-Raphson or any kind of numerical algorithm, starting with some initial thing. So here also, like
you start from somewhere, okay? Of course, you start from some place, and you try to find out this plane, right?
Also, we have to okay. Now I understand what we have to do. You have to decide like where to stop, how to decide.
Right. No, and more importantly, I mean,
how to turn.
How to turn.
Yes. How to turn. Yes.
How to turn. You cannot keep on turning. It's infinite size, right?
Yes, sir.
How to turn and yeah.
So is it also okay? So I think I interrupted you.
No, go ahead. Go ahead.
Okay. So I was saying, is it also a good feature to have where we are able to deal with these data points one by one rather than think of them as a whole?
Yeah, so that is also there. So many times what happens is that this data points comes in a stream.
Right.
Okay, so you have done some classification and something, right? And then the new data point comes and you have to kind of change it for that or something like that.
Right. So an ML algorithm would typically be something that could deal with the stream as well, right?
Again, so there are different applications of different things. Yes. So streaming algorithms, this goes into this world of streaming algorithms and so on.
But there are ML algorithms that don't
require. There are ML algorithms that don't do that.
Okay.
So of course, I mean, we are far from actual ML stuff.
Okay. Right.
But this is also the first course in algorithm. So
is it like this, like the assignment one coin problem that you were telling, like on a
See.
No, I'm like the feel of it. Like
yeah, you can try it. You can
if we can draw a horizontal line and a vertical line, so there will be some percentages of positives and some percentages of negatives.
Okay, there's two issues in this whole thing. Okay.
Okay, let us think.
Yeah, you guys think. Okay, there are two issues, and but one of the more important issues is that we are talking about in n-dimensional space. So don't just look at this picture and say that we are working in a two-dimensional space.
So it's like so many degrees of freedom, and in
Yes.
this two-dimensional case, there was just a single degree of freedom. So
yeah, so n-dimensional space is way more complicated.
Right.
Okay, so I want you guys to think about it. So tomorrow there is this tutorial session, right? From 7 to 8, right?
Yes, sir.
Yeah, I think I will take that class or tutorial, and in that I will do this problem. Okay, so I want you guys not to think too much, just for today or tomorrow, think about this problem.
Okay, sir.
Okay, and tomorrow we'll come back and see this problem algorithm as well as the proof. Yeah.
Okay. So will you be giving that assignment in?
Yes,
the
I will.
classroom?
I will post it.
Okay.
Post it.
Okay.
Okay. Okay. Good. So. Okay, so I will stop today. So let's meet tomorrow then.
Thank you, sir.
Okay. Yeah.
Thank you, sir.
Thank you.